Hey everybody, welcome back to our fourth and final video for lesson 2.2. I want to take a minute to remind us about dependent events and the formula that we were given. That formula brings in the conditional probability. In our last video, we found the probability of dependent events where we were using that conditional probability just by saying, hey, take out the man, take out the card. However, we also have another result of this conversation. If I'm asked to find the probability, the conditional probability, notice a little bit of algebra here. If I divide this to the other side, then the probability, conditional probability, is equal to my and divided by the probability of what was given. So conditional probability. The probability of F given E is equal to just the probability or the number of options for E and F combined out of the probability of what was given, aka divided by the number of options for the given. So let's use an example. Out of 300 applicants for a job, 212 are female, 110 are females with a graduate degree. So I have 300 total people. 212 they say are female. 110 they say are female and have a graduate degree. With that, what's the probability of a randomly chosen applicant that a randomly chosen applicant has a graduate degree given female? So they're wanting the probability of a grad degree given we already know the person is female. Well, what the formula says, I look at the number of options where I put the two things together. I have female and grad degree. I put them together. Divided by whatever was given. So in this case, the number of females. These problems, I'm going to be nice to you, and they will have already pretty much been in there. So female and grad degree, there's 110 out of the females I know I've already focused on. We can reduce that by 2 to get 55 out of 106, or as a decimal, 0.519. So in this conditional probability, it basically says that given is my new total. Let's do that again. Still same situation. I have 300 applicants total. 212 are female. 110 are female and have a graduate degree. B says if 152 of the applicants have a graduate degree, so total graduate degrees are 152. Keep in mind the difference here. This is female grads. If I'm looking at total graduate degrees, then that would include males and females. That's why there's a difference in those numbers. So they give me 152 people total have graduate degrees. What's the probability of being female given the graduate degree? So the probability of being female given, now the grad degree is my new total. So I put both on top, female and the graduate degree. But now the given is my new total. Female graduates are 110. Just grad degrees, 152. Again, I can actually reduce that by 2, giving me 55 out of 76. Or as a decimal, 0.724. So what that conditional probability lets me do is focus in on a specific characteristic that I already know to have been given. It's kind of like a guarantee. I already know this person has a graduate degree. What's the chances of them being female? They can either give the information to you within the problem, or they can do it from a table. So example 8, the table below shows the results of a survey in which 2,276 social media users were asked. So this is my total. Were asked whether they have been offended by something they saw on social media. Yeah, that's probably a really strong yes these days. Find the probability that a user is female. So I'm looking for the probability of female given the user was not offended. So by definition, I'm looking at the females who were not offended, putting those together, over my new total, the not offended. So the way I would read this chart, I look at females who were not offended. There were 549 people who were females and were not offended on social media. Out of, now I'm looking at the total not offended. So look down the no category, because this is the part I'm given. They were not offended. Females out of total. Let's reduce this one in the calculator. 549 divided by 1125 as a decimal or as a fraction. So 61 out of 125 or 0.488. About a 50-50 shot, almost 50%. All right, friends. So we have looked at a lot of things in this lesson. Independent, or the fundamental counting principle, independent, dependent, and now focusing in on that conditional probability. I have one more example for us where we're kind of just looking at some special cases. Please note that in this example, everything is independent. The reason I know that, the probability that a particular rotary cuff surgery is successful is 0.9, 90% chance of success. Y'all, this is independent because my surgery and your surgery are completely separate from each other, right? Mine being successful has no impact on whether or not yours can be successful. So what's nice about this, if I'm looking for the probability of 3 successful surgeries, so I want success and success and success, that's just 0.9. The probability of a success is 0.9 for each of them. I can shorthand that as my single success to the third power. So the probability of success with an exponent of how many successes you want. So in the calculator, 0.9 exponent of 3. It's a nice way to shorthand some of these calculations. We could have done this actually several times so far in this lesson. Like with our letters, 26, I wanted 6 of them. We could have shorthanded it. So if I had wanted 10 successful surgeries, I would have taken my success probability, raise it to the 10th exponent. So just be aware of that nice little shortcut. Find the probability that none of them are successful. If we wanted the probability of no success, then you have to use the complement rule. Remember from our previous lesson, the probability of no success is 1 minus the probability of success, 0.1. So if I'm looking for the probability of no success for the first surgery, and no success for the second surgery, and no success for the third surgery, I can look at just the probability of not being successful and raise it to the third power. So same concept as what we did in the previous example A, but this time not success, I have to use the 0.1. So that complement rule could come into play. Then I just go right back to that independence. Now, the last one, I'm going to put it on its own slide. Find the probability that at least one of the surgeries is successful. That at least one conversation is very unique. If I want at least one of something, that means I want all the outcomes except the case where there was none. Right? Think about it. 0, 1, 2, 3 successes in this example. If I want at least one, then I want 1, 2, or 3 successes. I want everything except no success. So we're gonna focus on this a lot in the coming sections, but if I want the probability of at least one success in those 3 surgeries, that's 1 minus the probability of no success in the 3 surgeries. So not just once. Here I just looked at one specific surgery. This is asking me if I want the probability of at least one successful surgery in the 3, then that's 1 minus the probability of no success in those 3 surgeries. Well, in that last example, we found that we would not be successful all 3 times in 0.001 situations, 1 out of 1,000. So the probability of at least one success for my surgeries is 1 minus that probability of none, 0.999. This is just a really useful rule or tool when we have independent probabilities. With that, friends, that wraps up this lesson. I know this was a bit longer with 4 videos, but hang in there. If you have questions about fractions or reducing, be sure you reach out. From here, we will continue probability. All of Unit 2 will be focusing in on counting my chances.